Okay, hello. This is assignment 1 for Physics 1215, the solutions. So, starting with question 1 here. The wave shown below is the resultant of two other waves being added together. On the blank graph below, please draw two different waves with a non-zero amplitude that could have created the resultant wave. So for this, there's literally an infinite number of big solutions. One of the simplest ones that I saw quite frequently is what I'm going to show. Pardon me, just letting the cat out of the room. So, here, I'll use green and blue just to make it distinct from the first wave here. And please mind my drawing. It'll be terrible. So, I'm going to choose my first wave to hit each of these points here. No particular reason. Okay, it's a little pointy for a sine wave, but it's good enough. So I've chosen my first wave to just be a regular sine wave with an amplitude of 2, which means my other wave is going to have an amplitude of 1, and it's going to have to be negative. And it will hit 0 at all the same spots so that it lines up nicely. And the amplitude is just going to be 1 so that when you add it together with the green wave previously put here, it ends up giving you back the red wave. So here we have positive 2 minus 1 gives us positive 1. The zeros all line up. And the same for here, we want negative 1, so we have positive 1 minus 2 gives us that negative 1 back. So that was question 1, pretty straightforward. On to question 2 here. A string of length 2 meters is fixed at both ends. Waves on the string travel at a speed of 36 kilometers per hour. Part A. Write the fourth wavelength that allows for resonance. So our resonance formula looks a little something like this. I have rearranged it already from our formula sheets here. So our resonance formula is given in, well, L in terms of lambda, but I have already rearranged it here for lambda in terms of L because we're looking for the wavelength. We are also told we are looking for the fourth wavelength. So that is going to tell me that I replace n with 4. And we're told that the length of the string is 2 meters. So I end up with 2 times 2 over 4. Lambda equals 1 meter. For part B, find the corresponding frequency for your answer in part A. So here we're going to be using the wave equation. V equals F lambda. We're looking for frequency, so frequency is going to be equal to V over lambda. We're not using C here because this is not light. It's not moving at the speed of light. We are told it's specifically a string and that the waves travel at 36 kilometers per hour, not at the speed of light. So we're using V instead of C. Small difference, but important nonetheless. Going ahead and plugging in. I have 36 kilometers per hour over 1 meter. Now, the units here, I need to change them a bit. I'm going to choose to convert kilometers per hour to meters per second. So, 36 kilometers per hour divided by 3.6 equals 10 meters per second. So that is going to be what I put back over here. So I get 10 meters per second over 1 meter. The frequency ends up being 10 hertz for this question. If you're unsure of where that 3.6 comes from, when I did my conversion for kilometers per hour to meters per second, please ask me in class or shoot me an email. Be happy to explain it. Number 3. A double slit experiment uses light of wavelength 500 nanometers. The slits are separated by 0.06 millimeters, and the interference pattern is observed on a screen 2.5 meters away. A particular bright fringe is found to be 6.25 centimeters from the central maximum. Determine the order M of this bright fringe. Okay, so first important thing I see here is that this is double slit. So, referring to our formula sheet, we're going to look for double slit. Now, we are asked for M. Both of these equations contain M, but we're told a couple of extra things here. We're told about the spacing. We're also told about how far away, what the distance to the screen is, the distance L. So we're going to be using this bottom equation here. X equals M lambda L over D. That is the one we're going to be using. So X equals M lambda L over D. That's what our equation is. Again, we are asked for M, so I'm going to rearrange this for M. So M equals XD over lambda L is our rearranged formula. And let's go ahead and plug in some numbers. For X, this was 6.25 centimeters. So I'm going to convert that to meters with the times 10 to the negative 2. D was 0.06 millimeters. The slits are separated by 0.06 millimeters. Oh, not M. I'm going to be converting this to meters now. So that is X and D. Lambda was 500 nanometers. So 500 times 10 to the negative 9. And L was just 2.5 meters. Hard meters, don't need to touch it. And this should give you exactly 3 when you plug it into a calculator. Should give you exactly 3. So that's questions 2 and 3. Moving on. Question 4. Now, the wording on this version that I'm currently solving has been edited. A few of us talked in class and worked on the wording a little bit so that hopefully it makes a bit more sense to everybody. So if this question 4 looks a little different to you, that's why. So question 4. Monochromatic light of wavelength 600 nanometers falls on a slit. So this is a single slit. If the angle between the two third-order bright fringes that are on opposite sides of the central maximum is 60 degrees, estimate the slit width. So, again, this is a single slit. So if we go to our formula sheet and look at single slit diffraction, we are going to be looking at one of these two equations here. We are told about M. We're told that this is third order. This second equation down here does not involve M, but this one here does. So we know we're going to be using this equation. It's just a matter now of whether we're looking for minima or maxima. So for us, we're told that this is the third order bright fringe. So let's take a look. Bright means this is going to be a maximum. So we are looking at this bottom sequence, and we are looking for the third order. So 3/2 is the first, second, third item in the list. We will be using 7/2 as our answer. So our formula is m lambda equals d sine theta. So m lambda equals d sine theta, and our m will be equal to 7/2. Okay, so now we are also told that the angle between these two bright fringes that are on opposite sides of the central maximum is 60 degrees. So if this is our setup that we're looking at here, we're told that this large angle is 60 degrees. However, we are only interested in half of this angle, which is 30 degrees. So our theta is just 30 degrees here. We're looking for slit width, so rearranging, I get d equals m lambda over sine theta. Subbing in, I get my 7/2 for m. We have 600, I don't know why I keep writing that, 600 nanometer times 10 to the negative 9. I'm going to convert this to meters for myself, over the sine of 30. Now, plugging this all in, you should get something about 4.2 micrometers, or about 4.2 times 10 to the negative 6 meters. Something around there. For question 5, a diffraction grating has 500 slits per centimeter and is illuminated normally with monochromatic light of wavelength 680 nanometers. What is the highest spectral order that can be observed? So we're looking for M. Something we need to do first with any diffraction grating question like this is we need to figure out what the slit spacing is. And to do this, we take 1 over the number of slits per meter. So here we have 500 slits per centimeter. Now there are 100 centimeters in a meter, so we multiply this by 100, and we end up getting 2 extra zeros there. So our D is going to be equal to 1 over 50,000, or 0.00002. So that is our slit spacing. That would be in units of meters, by the way. Using a rearranged equation for M, we get M equals d sine theta over lambda. Again, these are just formulas from the formula sheet. So if I look for diffraction grating, we have sine theta equals m lambda over d. I have just rearranged this for m by multiplying everything by d and dividing everything by lambda. So I get m equals d sine theta over lambda. We are also looking for the highest possible spectral order, which means that actually, I'm going to do this in a different color. So sine theta is going to be equal to 1. There we go. Now they're a little bit color-coded at least. So sine theta is going to be equal to 1. The maximum value of sine theta is positive 1. So this is the highest spectral order that we could possibly see. Guaranteed here. So again, D is 0.00002 times 1, if you want to still write it, over the lambda, which was 680 nanometers. And again, D is in units of meters here. So I'm going to put my wavelength into units of meters as well. Plugging this all in, we get about m equals 29.4 4, 1, 2, blah, blah, blah. I think that's rounded properly. I don't really remember what the actual decimal was. Not important though. The important part is that in this case we always round down. Even if this is 29.99998, for example, you still round down. The highest spectral order that is observable here is 29, not 30. Does not round up. So that was question 5. Question 6 now. How thick minimum should the air layer be between two flat glass surfaces if the glass is to appear bright when 120 nanometer light is incident normally? What if the glass is to appear dark? So here, I'm going to do light here. I'll do dark. Now, originally, on the first assignment I posted, the formulas, I had the light and dark mixed up here. My bad. I'm sorry. Now it is correct. So light is the one with the +1/2 in there. Okay. So we have our equations written out. Let's go ahead and plug in. I'm going to plug in 0 for M. Wavelength is 120 nanometers. I'm going to leave it in nanometers this time. And I end up getting, for light, 30 nanometers. For dark, plugging in 0 gets us, well, 0. I'll do this off to the side. T equals 0 over 120, or times 120, over 2. T equals 0 meters. This is the trivial solution. It also doesn't really work. If the thickness of the glass is 0, that means the glass is not there. And if the glass isn't there, then of course the surface below will be bright. It'll be lit up. So it doesn't work. So instead of plugging in 0, we're going to plug in 1. So we get 1 times 120 nanometers over 2 equals 120 divided by 2, 60 nanometers. So those were questions 4, 5, and 6. Question 7. A Michelson interferometer is illuminated with light of wavelength 550 nanometers. The movable mirror is displaced by 0.8 millimeters. How many bright fringes N are counted during this displacement? Our equation here is N lambda equals 2D. Rearranging for fringes, 2D over lambda, subbing in 2 times our displacement of 0.8 times 10 to the negative 3 to convert it to meters, and our wavelength in meters. Plugging this all in, you get about 2,909. Let's call it 0.1. So if you're going to round this off properly, just 2,909 whole fringes. Question 8. 3 ideal polarizing sheets are arranged in parallel planes. The second sheet has its transmission axis oriented 60 degrees relative to the first sheet. The third sheet has its transmission axis oriented 15 degrees relative to the first sheet as well. Unpolarized light is incident on the first polarizer. The question is, what percentage of the original light intensity emerges from the third polarizer? So, after the first polarizer, half of the original light will come through. That is because the original light is unpolarized, so half of it will be blocked, half of it will be transmitted. I2. This is going to be whatever light is coming from I1 times the cosine squared of the angle between them. So in this case, that is 1/2 I naught from the first equation there times the cosine squared of 60 degrees, which ends up getting you 1/8 times the original intensity. Now for the intensity coming out after the third polarizer, that is going to be whatever comes out of I2 multiplied by the cosine of the angle between the third and the second filters now. So from I2, I get 1/8 I naught times the cosine squared of, this time it is 45 degrees, not 15, not 60. We are looking for the difference in angle between the second and the third filter. So we don't take 15 degrees. That is the difference between the third filter and the first sheet. Instead, we take the 60 minus the 15, and that gives us the 45. That is the difference between the second and the third polarizing sheet. Plugging all of this in, we get about 1/16 times I naught, or writing this in decimal form, 0.0625 I naught. We're going to take a look at just this number here. 0.0625. Multiply that by 100%. We get 6.25% of the original light transmitted after passing through all the filters. So those were questions 7 and 8. Question 9. Unpolarized light that is traveling through glass and is incident on a layer of water at an angle of 48.8 degrees. The index of refraction for glass and water are 1.52 and 1.33 respectively. Now we're told that it's traveling through glass first. So this is N1, water second, that is N2. I put them in this order on purpose. Determine if the reflected light is fully or partially polarized. So this is a polarization angle question, where we have N2/N1 on the right and the tangent of the polarization angle, or Brewster's angle, on the left. Rearranging this, we get theta is equal to the arctangent of N2/N1, and plugging in numbers, we get 1.33/1.52. Plugging this all into a calculator now, we get about 41.2 degrees. So this is only partially polarized. Partially polarized, not fully. Number 10. What is the energy of the photons emitted by a 182.1 FM radio station broadcast? So first, let's get the frequency here. So the frequency of a 102.1 FM radio station, these are actually in megahertz as described in class. So this is 102.1 megahertz. We are looking for energy, which is equal to HF. So we're going to take Planck's constant H, 6.626 times 10 to the negative 34. Multiply that by the frequency, 102.1 times 10 to the positive 6. And the energy here for number 10 is about 6.8 times 10 to the negative 26 joules. I did not specify what energy unit to put your answer in, so I am accepting electron volts or joules interchangeably. There we go. 411. During a particular radioactive decay event, a nucleus emits a photon with an energy of 400 kiloelectron volts. What is its wavelength? How would you classify this photon? Is it a radio, microwave, infrared, visible, UV, X-ray, or gamma ray photon? Any of those? Talk about that in a second. Let's do the math first. So we know that we have energy and we're looking for wavelength. So we know that energy is equal to HF, and that if we replace F using our wave equation, this is also equal to HC over lambda. So we're going to use just the outer parts of this and smash it together like this. So this is the equation we're going to use. Again, just straight from the formula sheet. Now rearranging for wavelength. Here we have it. So let's plug in some numbers. 6.626 times 10 to the negative 34 times 3 times 10 to the 8, so that's Planck's constant multiplied by the speed of light, over 400. Now this is kilo electron volts, so that's times 10 to the positive 3 electron volts. Now, these are electron volts, so I need to multiply this by 1.602 times 10 to the negative 19. Reason being, Planck's constant has units of joule seconds, and our energy here was units of electron volts. So we need to convert either the top to joule seconds or the bottom to electron volts. Either way, no matter how you do it, you're going to end up with this extra factor down here, no matter how you do it. Try it both ways. Show it to yourself if you would like. Putting this all together, though, we get a wavelength of about 3.1 times 10 to the negative 12 meters, or about 3.1 picometers. And this is on the border between X-ray and gamma, but usually this would be described as a gamma ray. So typically an X-ray is greater than 1 picometer, and a gamma ray would be less than 1 picometer. So by this definition, it would kind of be an X-ray. Pretty much everywhere you look online, Google though, it'll tell you that it's a gamma ray, because it's very, very close to being 0 picometers, very, very close to being below. So it's on the fence. I accepted both answers as correct. I do think nearly everybody said gamma. Off the top of my head, I don't know if anybody said X-ray. If you did, I gave you the mark though. Moving on, last page, number 12. A metal has a work function of 3 electron volts. What is the wavelength of the lowest energy photon that will cause the metal to emit electrons? So we have a work function equation here, a work function question. You are not asked about the stopping potential or the kinetic energy at all. So we are just going to use this equation. I wrote out all the different versions of it here, just because. We are looking for wavelength, so we're going to take the far left and the far right side and use this here. Great. So we're told that the work function is 3 electron volts. We are looking for the wavelength of the lowest energy photon that will cause the metal to emit electrons. So this is just going to be whatever wavelength satisfies this equation when we plug in 3 electron volts. So rearranging, for a wavelength, because that is what we're solving for. We get this equation here. And now plugging in now, if I leave this as 3, again, this is in electron volts, and this is in joule seconds. So we need to convert exact same way as last time. And we get a wavelength of about 413 times 10 to the negative 9 meters, or 413 nanometers. There we go. Last question here. In a photoelectric effect experiment, it is observed that no current flows unless the wavelength of light is below 490 nanometers. Part A. What is the work function of this metal? So, just like before, we haven't been asked about the kinetic energy stopping potential at all yet, so we can go ahead and use this equation. We're looking for work function, so we don't need to do any rearranging. Just plug in right away. We are given 490 nanometers here as well. Now, the only units of energy I have are Planck's constant, so I don't need to do any converting between electron volts and joules at the moment. So plugging this in, I get about 4.0567 times 10 to the negative 19 joules. Now, I know, because I made the question, that electron volts are going to be way easier to work with. So converting this to electron volts, you should get 2.5 electron volts. Both of these are perfectly acceptable. There we go. Much better. Okay. Both of these were perfectly acceptable. So, now for part B. I'll color code these parts here. Each of them will get a different RGB. So B, what is the stopping voltage if light of 300 nanometers is used instead? And we are looking for the stopping voltage, or just the maximum kinetic energy that the electrons could have. So now we are going to be using our kinetic energy equation with the work function, which looks like this. We are given wavelength, so I'm going to substitute out frequency and use this version of the equation instead. No need to do any rearranging. Just plug in the numbers. Our wavelength this time was 300 nanometers. Great. So, the big difference here is that here we have units of electron volts. Here we have units of, and I should change the color because I'm about to use blue for something else. So here we have joules. So going to be converting so I'm converting this left-hand side to electron volts here. When I convert, just like I have been so far, I end up getting an answer of 1.6 electron volts. There we go. Just like in previous questions, we can take joules here and divide by our constant to get electron volts. So that is how I did it for both part A and now for part B here. Lastly, I'll fit part C in over here. What is the stopping voltage of light if 500 nanometer light is used instead? So if you see the shortcut right away, go ahead and use it. The shortcut is that 500 nanometers is longer than 490 nanometers. We are told that 490 is the minimum wavelength required for current to flow. So only smaller wavelengths will allow current to flow. Therefore, no current flow and / or no electrons being emitted. If instead you wanted to do the math, it is the exact same as for the part B in green. We get HC. I'm not going to write it out just for the sake of space, but this time it's going to be over 500 nanometers. Again, minus 2.5. Again, converting this and the kinetic energy for this one will be negative 0.02 electron volts. Now I did very briefly make a mistake earlier, so I'll fix that now. I used the wrong units in my green answer over here. So the stopping potential is not 1.6 electron volts. It's 1.6 volts. Small difference, but it's important. So that was everything for assignment 1. If you have any questions, please email me or ask me in class. Thank you.